Welcome to the Mathematicians Podcast, the podcast where we follow the fascinating stories behind the people that count in the history of mathematics. I'm your host, Benjamin Cornish, bringing you yet another thrilling tale from the annals of mathematical history. Today, our train of thought finally arrives at the station of the life and works of the man holding up the plane upon which sits the fundamentals of geometry. And no, having two overextended metaphors in a single sentence was not unnecessary for the magnitude of the figure we behold today. That's right, folks, Euclid. If you thought Plato was solid with his triangles, or Aristotle was demonstrably delightful with his logic, you're in for an all-encompassing delight. So let's edge straight towards it. Although first, I must read from the section of my script entitled Long and Tangentially Relevant Introductory Ramble. So I used to have a friend who was in the SAS, and he would always invite me on his multi-day treks. Imagine walking around the Scottish Highlands with nothing but your tent, sleeping bag, 40 kilograms of granola bars, and a shovel. Because when you're eating 40 kilograms of granola bars, you will need the shovel. On one of our trips, day 4 of 5, we had lost the tent. Let's just say one of us took it out of the bag to find the shovel and was then too distracted to put it back in some 20 miles ago. I wouldn't like to embarrass my friend, so let's just say it was me. "Don't worry, Ben," he said. "This happens all the time." He lied. Although I was still getting cold and nervous. "All we have to do is make it to one of the bothies." My podcast hosting provider tells me that I have 2 listeners in Scotland, which means that when I get one more, I'll be broadcasting to the entire nation. But for those of you unfamiliar with the area, the Mountain Bothies Association maintains about 100 bothies. These are rudimentary shelters, mostly stone or wood, with no reliable facilities other than a hearth for a fire. Tentless camping, if you will. These are all free at the point of use, and today I should point out my sponsorship deal. If you use code MathematiciansPod, then you can use the bothies 50% more free for a full night. At this point, my friend pulls out his map and says, "We just need to find our nearest bothy. Here's an old SAS trick. Find the points you think are near to you and draw perpendicular bisectors between each, then continue each bisector until they all meet up, dividing the region into tiles. That way, you always know you are closest to the point whose region you're in." He spoke with such confidence, but my nerves only grew. But we don't know where we are on the map, and there's no internet out here, so how can we tell which one is closest? "Oh, that's easy. I have an app which tells me which phone masts my phone is pinging for calls, and how long the delay is in the signal. We can use that to work out the distances from each tower, given the delay is proportional to distance, so we just draw circles on the map around each tower whose radii match the distances. Where those circles intersect, that's our location." He confidently checks the phone to find, you guessed it, no phone masts relaying the signal. Not only can we not triangulate our location, but we also cannot call for help. My anxiety was really starting to ramp up by this point. Okay, plan C. Check your compass for the beacon on the hill over there. The compass was with the tent. Oh, okay. Check the beacon against the mountaintop in the far distance. He held out his hand at arm's length and measured the gap between the peaks with his fingers, before cross-checking it against the map. Due east. So if we point a line on the map due west from that point, we must be on that line. Well, yes, but we have no idea how far away it is. At this point, he led us north for 1 kilometre in the direction he thought would take us to the nearest shelter. He checked the gaps between the peaks again with his fingers, did a quick calculation in his head, then said, "The beacon is 25 kilometres away." Oh, finally, I could parallax. But as we cuddled for warmth in the hut that night, it got me thinking. He did all that without any technology beyond a decent map. How old are these methods, and where did they start? Euclid was a Greek mathematician who lived around 300 BCE, working in Alexandria during the reign of Ptolemy I. For those of you who know your history, this puts him at the heart of the early Library of Alexandria. Unfortunately, history didn't leave us a treasure trove of personal details. We don't know when he was born, or when he died, or even what he looked like. He might have had a square jaw, or just been a well-rounded guy. What we do know, however, is that Euclid was a teacher, a thinker, and a meticulous organiser of knowledge. His most famous work, The Elements, became the textbook of geometry for over 2 millennia. And yet, he was never content to be preeminent. He dabbled in optics, astronomy, and even the theory of music. Basically, like all good librarians, he was into everything. Let's set the scene. Alexandria, the intellectual hub of the Hellenistic world, a city buzzing with scholars, scribes, and a library so big it made your favourite bookstore look like a leaflet. This was the environment in which Euclid thrived. He wasn't inventing geometry from scratch, much of it already existed. What he did was to organise it, refine it, and present it in a way that was logical, clear, and accessible. And trust me, that's harder than it sounds. If organising ideas were easy, then this podcast would come out daily. But before we get into the meat of the elements, let's explore Euclid's non-mathematical contributions. You might know of Euclid as the guy with the compass and straight edge, but his intellect wasn't two-dimensional. He contributed to several other fields, which we'll explore now. Euclid wrote a treatise called Optics, which studies how we perceive light and vision. His work gave a laser-like accuracy to the geometrical theory of optics, where he treated vision as a straight-line phenomenon. In other words, he believed we see objects because straight rays travel from our eyes to the objects. Of course, this is the opposite of how light actually works, but hey, even geniuses have a blind spot. Given that there are only 7 of them, I will read out all of the postulates from his work on optics. Let it be assumed. The rectilinear rays proceeding from the eye diverge indefinitely. That the figure contained by a set of visual rays is a cone of which the vertex is at the eye and the base the surface of the object seen. That those things are seen upon which visual rays fall, and those things are not seen upon which visual rays do not fall. That things seen under a larger angle appear larger, and those under a smaller angle appear smaller, and those under equal angles appear equal. That things seen by higher visual rays appear higher, and things seen by lower visual rays appear lower. That, similarly, things seen by rays further to the right appear further to the right, and things seen by rays further to the left appear further to the left. That things seen under more angles are seen more clearly. Ooh. Now, this is not wildly inaccurate and can definitely describe shadows and obscured vision, but notice the direction of the rays. Euclid is suggesting that the ray proceeds from the eye in a cone, and then anything that these rays touch can be seen. It does not posit a reflection of a ray, which might describe a modern radar system, just the connection of the eye to an object immediately. Despite the incorrect premise, Euclid's insights on angles of vision and perspective were invaluable for later thinkers. His ideas were reused for developments in optics during the Islamic Golden Age and the Renaissance. Without Euclid, we might not have had that beautiful geometric perspective in Renaissance art. He returned to the study of optics in another work called the Catoptrics. This treatise explored both the behaviour of light when reflected in mirrors, both flat and curved. In it, Euclid applied his characteristically rigorous approach, treating the paths of light rays as straight lines and formulating mathematical principles to describe how they interact with reflective surfaces. One of the central ideas in Catoptrics is the law of reflection, that the angle of incidence is equal to the angle of reflection. This might seem obvious to us today. After all, we see it every time we look in a mirror. But in Euclid's time, such principles needed to be explicitly studied and proven. He also explored how images appear in concave and convex mirrors, encouraging an enlargement in the future development in optics. Though Catoptrics itself didn't survive in its original form, its ideas were preserved and expanded upon by later mathematicians and scientists, including Islamic scholars like Al-Hazen and much later Renaissance thinkers investigating optics and perspective. In a way, Euclid's early studies in reflection paved the way for everything from the telescope lenses to modern physics' understanding of light. So the next time you check your reflection at those hideously misleading mirrors at the gym, or adjust your car's side mirror where the reflection may appear larger, you might just owe a nod to Euclid, or at least a well-angled glance. Beyond geometry and optics, Euclid also turned his attention to the stars. His work, Phenomena, is a treatise on spherical astronomy, a field concerned with the apparent motion of celestial bodies, as seen from Earth. It was an essential text in ancient Greek astronomy, serving as a mathematical foundation for understanding the night sky. At its core, Phenomena applies geometric principles to the celestial sphere, the imaginary sphere surrounding the Earth on which the stars and planets appear to move. Euclid systematically describes concepts like the rising and setting of the stars, the celestial equator, and the ecliptic, which is the apparent path the sun traces across the sky. Using rigorous logic, he demonstrates how different astronomical phenomena can be explained through geometry, much like how we use a coordinate system today to map out space. Basically, if you've ever used a star chart app on your phone, you're working with ideas Euclid helped to shape, just with fewer scrolls and more Wi-Fi. One of the key takeaways from Phenomena is that it reinforces the idea of a spherical Earth, a concept already gaining traction in the Greek world. By the 4th century BCE, philosophers such as Plato and Aristotle were arguing for a round Earth, citing observations like the curved shadow of the Earth on the moon during a lunar eclipse, and the way that ships disappear hull first over the horizon. Eratosthenes would later calculate the Earth's circumference with impressive accuracy, using nothing but shadows and basic trigonometry. By Euclid's time, the scientific consensus was firmly on the side of a spherical Earth, though, as we know all too well today, some people just never get the memo. What makes Phenomena particularly significant is Euclid's use of spherical geometry to describe celestial movements. Unlike the straight lines and flat planes of his Elements, this work embraces curved surfaces and arcs. Ironically, the term non-Euclidean geometry today refers to mathematical systems that depart from Euclid's postulates, such as the hyperbolic or elliptic geometry. But in reality, Euclid himself was already working with curved spaces when mapping the heavens. So while modern non-Euclidean geometry is named for what Euclid didn't do, the joke's on us because he kind of did. This work became an important reference for later astronomers, including Ptolemy, whose Almagest built up many of the same principles. It also influenced medieval Islamic scholars, who refined spherical trigonometry to improve astronomical calculations. Even today, spherical geometry remains vital in everything from GPS systems to astrophysics. In other words, Euclid was more than just triangles. He was helping us navigate the cosmos. Not bad for a guy working without a telescope. Once again, with Euclid, as I have been prompting for months now, the work is arguably not his own. As we saw last week, Autolycus had published a very similar text on the moving sphere. When people think of Euclid, they usually picture his towering influence on geometric construction, but his contributions extended far beyond just shape and space. Among his lesser known yet deeply insightful work is Data, which survives today, a treatise focused on the idea of known and unknown quantities in geometry. But alongside it, Euclid also wrote Pseudoria, which literally translates as fallacies, and also he wrote porisms, or corollaries or propositions, which further developed mathematical reasoning, proof structure, and the identification of errors in logic. These works, though now lost or surviving only through later references, offer a glimpse into Euclid's role not only as a teacher of mathematics, but as a defender of mathematical truth. Essentially, Euclid wasn't simply proving theorems, he was making sure no one got away with bad maths. At its core, Data explores the conditions under which geometric information can be considered given, i.e. known and fixed. and how this information can be used to deduce further results. This book consists of 94 propositions, each stating a relationship between known and unknown values. For example, if you're given a fixed angle and one side length in a triangle, you can determine other properties of the figure. This method of working from known data to uncover unknown relationships became a standard operating procedure of mathematical reasoning. It's essentially ancient Greek detective work, but with fewer dramatic plot twists and more right angles. While data helped clarify what can be deduced from known information, pseudoria was concerned with what couldn't. As its name suggests, pseudoria, which we say is fallacies, was dedicated to exploring mathematical errors and misconceptions, something of an ancient Greek debunking manual. Though the work itself has not survived, later references suggest it was an instructional text aimed at helping students avoid common logical mistakes. This suggests that Euclid wasn't exclusively interested in proving what was true, he was also deeply invested in proving what was false, which, if we're being honest, is something modern internet discourse could still use. After all, if it's not a right angle, it's a wrong angle. The third related work, porisms. It's a bit of a mystery. The term itself is tricky to translate, but it's often rendered as corollaries, these auxiliary propositions. It seems to have been a collection of intermediate results that were useful in solving problems, but weren't full theorems of their own. The 3rd century mathematician Pappus of Alexandria, who commented on Euclid's lost work, describes porisms as being somewhere between a theorem and a problem. Statements that revealed deeper geometric properties without necessarily being constructive proofs. Though we may never know its full contents, this work hints at Euclid's interest in laying down a structured, almost algorithmic approach to problem solving. Like much of Euclid's work, these texts were widely studied throughout history, particularly in the Islamic Golden Age and the European Renaissance. Mathematicians like Pappus of Alexandria and later European scholars used them to refine their understanding of geometry, leading to a more formalized algebraic methods and a more uniform approach to problem solving. Let's just say Euclid gave us the data, but not necessarily the answers. Euclid didn't only build up the wealth of constructions, he was also fascinated by how we break things down. One of his lesser known but intriguing works is Divisions, or On the Division of Figures, a treatise focused on the art of cutting geometric figures into specific proportions. While the original Greek text has been lost, a partial Arabic translation survived, preserving a glimpse of Euclid's approach to a fundamental mathematical challenge: how to divide geometric shapes according to given conditions. Basically, if you've ever argued about how to fairly slice a pizza, Euclid was way ahead of you. The main objective of Divisions was to show how a given figure, such as a triangle, quadrilateral, or circle, could be divided into parts that satisfied certain constraints. These constraints could be proportional, e.g. divide this rectangle so that one part is twice the area of the other, or positional, e.g. cut a triangle through a given point. This work was deeply practical, laying the groundwork for later advances in fields like surveying, architecture, and even modern computational geometry. Euclid's methods ensured that divisions were not just approximate, but provably correct, reinforcing the idea that mathematics could provide exact solutions to spatial problems, which is probably why mathematicians still love dividing things into neat logical sections, even when real life is rarely so cooperative. At this point, I might give you a sneak preview about an upcoming episode where we interview a mathematician who developed a game about Euclidean geometry where you have to solve puzzles involving cutting up geometric shapes or constructing geometric shapes. Much of this is based on Euclid's work, divisions being a big part of this, and if you want to play the game ahead of next week's interview, you need to go to euclidia.xyz. One fascinating aspect of divisions is how closely it aligns with the classical Greek obsession with proportionality and harmony. The Greeks, especially thinkers like Pythagoras, believed in a deep connection between mathematics and aesthetics, and Euclid's work in divisions fits right into that tradition. The ability to divide figures in precise ways had applications in everything from classical art to land distribution. In other words, if you were an ancient Greek landowner and you wanted to make sure that your neighbour didn't get the better half of the vineyard, Euclid had your back. Also, this topic has been a particular fascination for me, which I shall share now. I grew up with two brothers who did not like to share food. Sadly, there was a frequency where only one muffin was left, and two brothers who might have been hungry. Our solution to this conundrum was I cut, you choose. Essentially, one brother, and it didn't matter which, would cut the treat up, and the other brother would choose the half they thought was bigger. The cutter is happy because they believe they have cut it into equal parts, and so will be content with either, and the chooser is happy as they believe they got the greater half. However, occasionally, all three brothers would want to share the same item. So how do you organise the cutting and choosing process so that no one feels like they have been shortchanged? Well, I will leave that as a protocol for you to figure out on your own. The influence of divisions didn't end in antiquity, or indeed my kitchen. The preserved Arabic translations ensured that the text remained part of the medieval mathematical curriculum, influencing scholars in the Islamic Golden Age. Later, during the European Renaissance, mathematicians revisited these ideas, incorporating them into developing fields like projective geometry and calculus. Today, the principles Euclid outlined in divisions are still relevant in fields like computer graphics, engineering, and data visualization. Whenever a complex shape needs to be broken into meaningful parts, think triangulation of the surface onto a computer model, or my SAS friend dividing the terrain into regions closest to that individual point. Among Euclid's other lost work, we have surface loci on the places of surfaces, and conics, or on conic sections. These stand out as tantalizing glimpses into the contributions to more advanced geometry. While neither text has survived, later mathematicians, particularly Pappus of Alexandria in the 4th century CE, referenced them, suggesting that Euclid was deeply engaged in understanding curved surfaces and higher dimensional geometric relationships. Surface loci likely dealt with the conditions under which points could lie on specific surfaces, extending the idea of loci, sets of points satisfying given conditions, from lines and planes into three-dimensional space. This would have been an early exploration of what we now call differential geometry, setting the stage for later studies of curves and surfaces. In short, Euclid wasn't only thinking in straight lines. Conics, on the other hand, was Euclid's foray into the study of conic sections, ellipses, parabolas, and hyperbolas, formed by slicing a cone at different angles. While the definitive work on conics came later with Apollonius of Perga, who expanded the subject into conics, Euclid's lost treatise suggests that he had already begun systematizing these curves in an earlier form. Given that the conic sections later became fundamental to physics, orbital mechanics, and even the design of a telescope lens, Euclid's role in shaping early conic geometry was likely crucial. If only his book had survived, we might have been spared a few centuries of mathematical catch-up. Now, I've been making you wait for the good stuff, because I wanted to highlight how Euclid is not a one-trick pony. But it must be acknowledged that he is primarily known for one single work. So let's dive into The Elements, Euclid's magnum opus. This was no ordinary maths textbook. It's a mathematical epic. Imagine if Tolkien had written about triangles instead of hobbits. The Elements is divided into 13 books, and each book covers a specific area of mathematics. Books 1 to 6 cover plane geometry, 7 through 9 are number theory, Book 10 works with irrational numbers, and books 11 to 13 deal with three-dimensional geometry. What sets The Elements apart is its methodical structure. Euclid begins with definitions, axioms, and postulates, basically the building blocks of geometry, and from there he constructs proofs, step by step, like a meticulous architect building a cathedral of logic. If you've ever suffered through a geometry class where you've had to prove that the triangle's angles add up to 180 degrees, you can thank, or perhaps blame, Euclid. He's the reason your high school notebook was filled with triangles and frustration. Euclid's definitions are a masterclass in clarity. Take this gem. A point is that which has no part. It's simple, elegant, and leaves no room for misunderstanding. He also defines lines, planes, and angles in similarly precise manner. If only modern instruction manuals were this clear, assembling furniture would be a breeze. Euclid's 5 postulates are the foundations of his geometry. The most famous, of course, is the 5th postulate, also known as the parallel postulate. It states, if a line intersects 2 other lines such that the sum of the interior angles on one side is less than 2 right angles, the 2 lines will meet on that side if extended far enough. This postulate baffled mathematicians for centuries. It's not as straightforward as the others. And attempts to prove it from the first 4 postulates eventually led to the creation of non-Euclidean geometry. More on that later. Don't get hyperbolic on me yet. To appreciate Euclid's work fully, we need to understand its context and its influence on modern mathematics. Euclid didn't invent geometry, but he refined it and organised it. He built on the works of the earlier mathematicians like Thales, Pythagoras and Eudoxus, but whilst those thinkers set the stage, Euclid was the actor on that stage. His method of deductive reasoning set the standard for mathematical proofs, a tradition that continues to this day. The Elements remained the primary textbook for teaching geometry for over 2,000 years. Think about that, 2,000 years. That's like your great-great-great-great-grandparents using the same maths book as you. It was translated into Arabic during the Islamic Golden Age and later into Latin, influencing scholars across cultures. Even today, Euclid's work underpins much of modern geometry. His logical structure inspired not only mathematicians, but also in fields like philosophy and physics and computer science. The concepts of axiomatic systems, where you start with basic truths and build upon them, is now a cornerstone of modern logic and programming. So yeah, Euclid was basically the OG coder. Now let's talk about the elephant in the room, non-Euclidean geometry. For centuries, mathematicians wrestled with Euclid's 5th postulate. It didn't seem as self-evident as the others. The idea of a postulate or an axiom is something that has to be taken as true or not on its own terms and not justifiable by other statements. But for many, many years, mathematicians were trying to prove the 5th postulate from the first 4, and this led to the revelation, well, what if that's not the case? What if it is a postulate, and therefore, what if it can be taken as true or not true? In the 19th century, mathematicians like Lobachevsky and Riemann developed geometries where the parallel postulate didn't hold. These non-Euclidean geometries opened up entirely new ways of thinking. They're crucial for understanding curved spaces, like the surface of a sphere or the fabric of space-time in Einstein's theory of general relativity. So in a way, Euclid's limitations led to some of the most groundbreaking advances in science. Talk about turning a blind spot into a bright idea. So why should we care about a guy who's been dead for over 2 millennia? Well, it's because Euclid's work is everywhere. In education, geometry is still a core part of the maths curricula worldwide, and much of it is based on his methods. In architecture and engineering, the principles of geometry are foundational in designing buildings, bridges, and even roller coasters, thanks to Euclid for making sure our skyscrapers don't lean like the Tower of Pisa. In technology, computer graphics, game design, and simulations rely on geometric principles. Every time you marvel at a stunning CGI scene, you're witnessing Euclidean geometry in action, albeit with a touch of non-Euclidean flair. In science, from mapping the human genome to exploring the cosmos, geometry is the vital tool in modern science, and it all traces back to Euclid's pointedly brilliant work. Euclid's contributions to mathematics and beyond are a testament to the power of clarity, logic, and systematic thinking. He didn't just teach us how to measure angles or calculate areas, he showed us how to think rigorously and build knowledge step by step. So the next time you draw a simple triangle, marvel at a painting, or use GPS to navigate, remember Euclid. He might not have had the flashiest life story, but his work has stood the test of time. And for that, he truly is the father of geometry, and perhaps the ultimate proof that maths is indeed a universal language. Thanks for joining me on this mathematical journey. If you'd like to hear more from me or get in touch to ask advice on how many friends you should share this podcast with, you can follow me on Blue Sky at mathematicians-pod. Next week we have an unbelievably exciting episode, another in the sub-series of Injectives, and one I've been looking forward to since starting the show. I sit down with one of my favourite games designers, who just so happens to have developed one of my favourite games. It's the co-creator of Euclidia, coming in to answer all of my questions about Euclidean constructions and the game. Before you listen along, head over to euclidia.xyz to play the game for free and get a sense of why I was so excited to speak to its creator. Until then, goodbye! The music today is Danse Macabre Finale by Kevin MacLeod. You can find more information in the show notes.